Okay, we'll get started. Today's lecture will continue on data structures in R, and so I think today we'll get to cover kind of the rest of our one-dimensional data structures, and then and I guess Wednesday we'll start covering the two-dimensional ones, matrices, data frames, and things of that nature. How's everybody doing? Okay. It's our first week of class, right? So everything's going well. We're getting lots of sleep at night. Yeah. Okay. Make sure you get lots of sleep every night, right, for the duration of the quarter. I think we left off on Friday talking about coercion, and we said, you got a logical vector. You do a mathematical operation on it. It's going to coerce everything, all of those values, to zeros and ones, which makes things like calculating the mean, calculating the proportion that's true, to be really easy, because the trues get coerced into ones, the falses turn into zeros, and you ask, now you have a vector of ones and zeros, and you ask what's the mean, it's going to tell you the proportion that is 1. Okay, and that happens automatically, but we can explicitly coerce things into certain data types if we want. So you can turn things into logical vectors into Booleans by using the as.logical function. As.logical is going to turn basically anything that's not a zero, okay, any numeric value that's not a zero, into true. And if you say as logical for a 0, then it will turn into false, okay? As.logical is also able to coerce character strings into true or false, and it will do true, capital true, and lowercase true. It will coerce those into true, right? And then likewise the false variants of those. Whereas if you give it a character string that's not something like that, then it will say, I don't know what you're talking about, and it will return a missing value. Okay. We can coerce things into integers, okay? Integer, the function as.integer will always kind of truncate decimal values towards 0. So if you ask to do as.integer on pi, it just drops everything after the 3. So it's not rounding. Okay, if I did as.integer 3.9, it's going to just drop the 0.9 and return back at 3. Okay. It can also coerce character strings that have numbers in it, right? So if you have a character string, something like this, it's got something 0.9 and white space, it's going to drop the white space, it's going to drop things after the decimal, and it turns this into here, okay? However, your computer has a limitation, okay, right? There's an infinite number of numbers, and you only have finite amounts of memory, and so as far as the integers go, this is actually the largest integer that your computer can store, okay? So as far as integer type goes, this is the biggest integer it can store. And you can find out what that number is by typing in .capital machine, and then you can just hit enter and it lists off all the machine information. And if you want the integer, you can do $integer max. It's inherent to your chipset, okay? So pretty much everybody uses an Intel chip, right? If you got a Mac, it's an Intel chip, and pretty much everybody's Windows computer is an Intel chip. Maybe a few of you have an AMD chip somewhere inside your Windows machine, but they're not as popular, okay? And so, and I think they use kind of the same instructions also. So this is inherent to the chip CPU of your computer. It's so Windows and Macs will have the same as far as this thing goes, okay? But if you try to coerce a numeric value bigger than the integer max, it's gonna give you an NA, all right? It's gonna say, warning, NA is introduced by coercion into integer range. That says the thing you're doing is outside the integer range, therefore we're going to say it's a missing value, it's NA, okay? Try to, rather than give you the wrong integer value, okay? What's the difference between a warning and an error? Yeah, so if you've got a bunch of code and you've got like a script or something and there's an error, then your script stops, okay? It's not going to keep running the rest of your code. A warning, it will keep running, but it sends a warning to the screen and says, you know, you better check your results to make sure that what you're looking at is what you are expecting or want it to be, right? So sometimes, you know, we want to ignore the warnings, but don't. Generally, it means you better check your results, okay? And for all of these things, you can always just do question mark as.integer or something to find, you know, read the help, the details to see exactly what it's doing for those things. Okay, as.character pretty much just puts quotes around whatever thing you're looking at. Okay, so if you say as.character true, it just puts quotes around true. Okay, and if you give it a number, say as.character pi, it's going to keep about 15 digits there. Okay, and I think the machine precision is usually around 17 digits, and that's just to avoid any kinds of possibly having the wrong number in there when you do a as.character thing. But if you want maximum possible precision, you can use format, but that last number may not be as reliable as you might want it to be. But, you know, I don't know how often we need more than 15. Well, the people who made the chipsets decided 15 decimals of precision is pretty accurate. So, okay. And then we also have as.double, as.numeric. As.numeric is the same as doing as.double, okay? I think our computers even have an as.single, but there's no single value type. So as.single is exactly the same as as.double. It's here. Now let me just back up my claim. Is there an as.single? There is an as.single. And maybe it's different, but I'm pretty sure if I do as.single false, okay, that's what it returns. So if I say type of, it's type double. Okay, so as.single returns a 0 of type double, but it comes with an attribute that says it is a C single type. Okay, so if you were doing something with the C language, you can kind of remember what that does. But okay, but it's the same. All right, as.double, that's probably the one we want to use. And pretty much you'll use as.double if you got like character strings or factors and you want to turn them in. No, just character strings. Okay, character strings, it'll turn the characters into numbers, but it doesn't understand plain English words. So this will, if you try to turn something like this into as.double, it will return back a missing value, NA. Okay, so all of this talk about NAs is means that NAs represent missing values, okay? And we have different NAs for the different vector types, okay? So yeah, NAs are whenever you have, you know, kind of your vector of values, and if something is missing, we store that and we say it's a missing value by using NA, okay? If we ask type of NA, it's going to give me logical. Why is the NA type logical? All right. Well, let's just see what happens here. Okay. Let me I'm gonna clear out what we have here. Okay. So if I have C 1, 2, and 3. Okay. And if I say, what is this type of? What type of data is this? It's double type, right? Okay. Type of default numeric type in R is double, okay? And if I throw in an NA here, Okay, this NA is, earlier we saw NA is logical. Okay, so here I throw in a NA, what's going to happen? The NA will get coerced into type double, and so this entire thing is type double, right? Because in an atomic vector, everything has to be the same data type. And so we actually have different, oops, not NA double, it's NA real, is what we have. We have different NA types. We have NA underscore character, NA underscore different things here. So if I did, if I took 1, 2, 3, and then I fed in NA underscore character, what is this going to do? It's going to coerce everything into characters, and so now I have 1, 2, 3 as characters and the missing value here. Okay, so we start off with the logical NA of type logical, and then when we do operations to it, it just coerces the NA into other types, right? So if this way I can have true, false, and NA, and this will be type logical. So that's going to be type logical, whereas if I stuck in NA real in here, then everything gets coerced into type double, and it will return back double there. Okay, so this NA gets, this operation, the addition operation, looks at the 1, it looks at the NA, it coerces the NA into double, and then so when we ask the type of the result, it's type double. This NA right here, that's what this is. This is now double type. Okay. If we ask, is NA equal to NA? The answer there is NA. It's missing. Okay, so it's not. You can't check to see if values are missing by saying, is it equal to NA? Because anything equal to NA is always going to return a missing value, right? So if we say, is 3 equal to NA, what is this? This is going to say, I don't know, all right? False equal to NA, it's going to give NA, right? NA equal to NA is NA. So if what you need to do is you need to do is.NA, and that's going to return true, okay? So is.NA on NA will return true. If I do is.NA on this, let's just use regular old NA. Okay, then it says this is not missing, missing is true. Okay. All right, you throw in NA into this 4, 5, NA 3. It's going to say 4, 5 missing 3. Okay, and then you can, again, we have different NA types. We have it's a little bit confusing, but it's NA real rather than NA double. Okay, but that's what we have. Okay, so you throw in a missing value, that's going to do that. Okay, similar but different. Okay, distinctly different from NA is the null object. Okay, so here we had missing values represented with NA. On the other hand, we have null. Null is the null object. Null is for values that do not exist. Okay, there's a difference between a value is missing and something to say that this object does not exist. Okay, when the object does not exist, we get null, not missing. Okay, missing means we're kind of expecting something there, but it's just not there. Okay, so if we ask the type of the null object, it returns and it says this is the null object. Okay, and you have to ask, you use the question is.null to test something. Is it the null object? Okay, it's not is it missing, is it NA? That's going to give us null. Okay, and if you try to do something like is 3 equal to the null object, it's going to return back a logical vector length 0. Okay, logical 0 is a logical vector. Okay, so but the vector is of length 0. So this is a 0 length vector, so it just means there's nothing there because this equal operation is going to return logical values, right? You're testing for equality, so it's either going to give you true or false or missing, but when you're testing it against the null object, it says, well, there's nothing. This thing doesn't exist, so it gives you back a logical vector of length 0, okay? And is.na on the null object also gives you logical of length 0, right? Is.logical on null, is the null a logical object? No, it's not, okay? What's happening here, if I do null plus false, why am I getting integer 0? Null plus false. So what happens, okay, false is a logical value, right? But then the plus operator, what does it do? It coerces the false into an integer value. Okay, so when you use the plus operator, it turns the logical things into numeric types, and it's going to first go into integer type. And so we have integer type, and then we're adding the null object to an integer. Here it's going to be 0, but it says, you know, I can't do that, so it returns back an integer vector of length 0. Okay, and then if I throw in the null object into some vector here, I got 4, 5, comma, null, comma, 3, I just get 4, 5, 3. Okay, so this vector, okay, this thing, what is the length of this? The length is 3, and I can ask, is it identical to 4, 5, and 3? Okay, and the answer is true. Okay, so 4, 5, null, 3 is exactly the same as 4, 5, 3. Okay, the eyes of the machine. So these are the same. We're putting in the null object. Whereas if I have the missing thing, okay, this is not, right? Because 4, 5 missing 3 is distinctly different from 4, 5, 3. Okay, we have other special values. Not a number, NaN, and infinity and negative infinity. These are all double types, okay? These things are stored in the computer as type double, and those are just kind of values that are inherent to the way the computer stores floating point numbers. Okay, so when it stores floating point numbers, it also has a way to store not a number, infinity, and negative infinity, and those are there. Okay, we don't always get what we expect. Okay, and don't try to use the computer to define like rules of math. Okay, the laws of math it doesn't depend on what the computer says, right? So pi divided by 0, it gives us infinity. We maybe asymptotically that might be true as you do pi divided by x as x approaches 0 from the right. Then yes, you would get positive infinity there. But you can't divide by 0. That's like against all rules of math, and so I guess it's one rule of math, but you can't do that. And so, you know, and then 0 over 0 says it's not a number. Don't say use these to like define the rules of math here. Okay. So anyway, you know, what's infinity plus negative infinity? It says, yeah, we can't do that. Okay. I was gonna give you a quiz, but this is it's kind of hard. So we'll just go through the answers. Okay. So if I combine 1 and I have the missing value and the capital letter C, what's this going to give me? Okay, it's going to give me, it's going to coerce everything into character type, okay, and then the missing value remains missing. Okay, so this is character type. If I take the integer 1 divide by 0, that's going to give me infinity, and then the missing value is NA, so that's still there, okay? But again, infinity is type double, and so this will say it is type double, okay? If I combine the integers 1, 2, 3, and the value 5, and so we just get this, but the value 5 is type double, so this is going to be type double as well. All right, over here I've got the integer 3, and then I'm going to add the integer 1 to not a number, okay? So I get 3 and not a number, okay? Adding, you can't add stuff to not a number, all right? So you're still going to get not a number, okay? But not a number is type double, so everything gets coerced to type double, okay? NA and true, NA is logical type, okay? So the NA that you use is base logical type, and then it just gets coerced to the higher versions of NA if you need it to be, okay? And here, so this is type logical. Oops. Is that okay? All of this combining coercion and missing values and null objects. You got a few exercises in the homework. Oh, I posted, so, well, maybe we'll take a small detour. I posted homework 1, okay? And that will be due on Friday, okay? Friday at 6 o'clock. And here's the templates there. You're just going to download that, the RMD file. You'll work on it. You will render it as HTML, and you'll upload your HTML file back into to homework 1, okay? And then I have avoid grading issues with the homework. This just, I think I talked about this on Friday. Basically, just make sure the results of your code is made explicitly clear for the grader to see. Okay, so yeah, homework 1 has been posted. All right, we've got many operators work element-wise. Okay, so kind of our mathematical operators, plus, minus, division, all of that stuff. So here I've got 1:4, so those are the integers 1, 2, 3, 4, and then 2:5, 2 through 5, and if I do addition, it's going to do 1 plus 2, 2 plus 3, 3 plus 4, and 4 plus 5, so I get 3, 5, 7, 9. Okay? And then if you do multiplication, you get the same type of thing. You get 1 times 2, 2 times 3, 3 times 4, and 4 times 5, and so you get 2, 6, 12, and 20. All right, and so if you see this like some Facebook puzzle, right, and they ask what's the next in the sequence, you would say blah, 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 right? 5 times 6, 30. You are smarter than 80% or whatever. Here we have recycling elements, okay? And maybe we've seen this, maybe we haven't. So if you have the vector 1 through 4 and then the vector 2, 3, okay, it's going to recycle those elements 2, 3. So it's going to do 1 times 2, 2 times 3, and then it goes 3 times, and then it's run out of the first vector, or the second vector, so it goes back and it comes back to the 2. Okay, so it goes 3 times 2, and then 4 times 3, and so you get 2, 6, 6, 12. And it does that even if they're of different lengths, okay? So if I have 1, 2, 3, 4 as our first vector and 2, 3, 4 as our second vector, it does 1 times 2, 2 times 3, 3 times 4. It's reached the end of the end of the second vector, and it loops back around to a 2. Okay, so we get 4 times 2. But then it gives us a warning, and it says, warning, in this thing that you just asked me to do, the longer object length is not a multiple of the shorter object length. Okay, so it says, you know, I went 1, 2, 3, 4 over here, and then I go 2, 3, 4, and then I looped around and I got to the 2, and then I ran out of numbers. Okay, and it says, well, that's weird because I still had the 3 and 4 left over. You know, so it says I did it, but I'm not sure if this is what you wanted. Okay, so it gives you a warning here. Okay, and so sometimes that's good, right? A lot of times this might point out like, oh, maybe I did something I wasn't expecting, or maybe this is exactly what you wanted it to do. You know, if we had 1 through 6 over here, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, and then we had 2, 3, 4, 2, 3, 4, then it would match up and it would not give us any kind of warning. But perhaps that's also not what you wanted. If you wanted something like 2, 2, 3, 3, 4, 4, you can't do the operator like this. How would we get 2, 2, 3, 3, 4, 4? We'd have to use a function like repeat, okay? So there's the repeat function, and we can do 2, 3, well, here, I'll just, so I got 2 colon 4, comma 2, and that will do 2, 3, 4, 2, 3, 4, or you can do each equals 2, and then it'll go 2, 2, 3, 3, 4, 4, right? And then we can do 1 through 6 times this, and then there you go. 2, 2, 3, 3, 4, 4. Is that right? Yeah, okay. Okay, now let's talk about lists. Lists are still considered as vectors in R. They're considered generic vectors. And the difference is that in an atomic vector, everything had to be the same data type, right? You've got characters, then the whole thing has to be a character vector, okay? With lists, you can have different variable types. So you can have, or data types. You can have character data, you can have logical data, you can have double type double or whatever. You can even throw in a function or something else, okay? Just any kind of object you can throw into a list, okay? And so here, if I look at this, I've got list A, true, false, 1 through 4 divided by 2, and then the function, and we can see I've got 4 things in my list, okay? The double bracket 1 shows that the first thing in my list, then I've got double bracket 2 for the second thing in my list, third thing in my list, and fourth thing in my list. So the first object in my list is a character vector of length 1. The second object in my list itself is a vector with 2 elements in it, and it's a logical vector. And the third thing in my list is a vector of length 4. Okay, and then the fourth thing in my list is a function of x. Okay, and so here I've got the list of four things, and then it says the first one's a character vector, logical vector, numeric vector, and then we have a function. Okay, you can embed lists inside of lists, right? And these lists will not be flat. When we did this with atomic vectors, if I tried to put, combine something inside another thing and I put them inside, then it just flattened the whole thing, right? Everything was still just in one vector. Now, if I have a list, I'm going to create list B, and I've got to create list C here, and then I'm putting, I'm not following my own rules of not naming anything as C, but I'm not creating a function called C, so R will, if I use the function C, R will understand that I'm not referencing the list here. But if I created a function C, I'd be in trouble. But so here I've got B is a list of 2. The first thing in B is a numeric vector or a double vector of length 1, and the value is 5. And then the second object in list B is a double vector of length 1 where the object is 12. Okay, and then list C has only one element in it, and that's a double vector of length 1 where the value is 13. And I'm combining those 2 lists into object A. So I've got list A, which is B, has 2 objects in it, list B and list C. And so this appears like this, and all of these double brackets look kind of confusing, but this just means here is the first object in the list. The first object in the list itself is a list, and so this is the first object in list A, and within that first object, we're looking at the first object in that thing, okay? And that is a vector of length 1, and the item is 5, okay? The square 1 here just means the first item in this vector, okay? And so it comes out, it makes a notable difference if you have something like 1 through 200 or something. Okay, first item is a 1, the 21st item is 21, and the 181st item, that's just kind of, it's a way to display it. Okay, so we have this, right? And so when we go through, we've got the structure of A is a list of 2 objects, okay? And we can see those 2 levels. And the first object itself is a list of 2 with a numeric vector and another numeric vector. And then the second object in the top level list is itself a list with 1 object with a numeric vector with the object 13 in there, value 13 in there. We'll get into the subsetting in a future lecture, either tomorrow or the one after. Okay. All right. So when you combine lists, okay, things don't always do what you expect. So here I've got list 1, 2, and then 3, 4. So this itself is a list of 2 objects, okay, and then I've got a numeric vector 3 and 4. Okay, and if I throw that into a list, now I have a list of 2. I've got a list of the 2 objects 1 and 2, and then the numeric vector 3, 4. Okay. However, if instead of using list, I use C combine on the exact same insides, the behavior is a little bit different. Now I get a list of 4, and I've got 1, 2, and then it has kind of coerced this numeric vector of 3, 4 into list type, and now we have 1, 2, 3, 4 here. Okay, so this is, you know, oftentimes using combine where the insides are lists might not give you the behavior expected, okay? You might have expected because it coerces the other things into list type. Okay. With lists, we can name things. We could name things back in vectors also, but we can also name things in lists, and this is very useful because oftentimes our lists are complicated. And so you just you define them using, you have to use the equal sign when you're using names. Don't use the arrow, okay? The less than dash, the arrow. Don't use this, what do we call this thing, okay? So we have A equal to 1, B equal to this, and all of that. And so, so when we look at this, we've got the list, and we can see the names appear in the structure of our list. We got A, B, and then C is names inside of list B. C and D are names inside of list B, and then we got E, which itself is a vector. Okay. So if I wanted to ask what is object A inside list, the object example, which is a list, I can do examp $A, and it's going to give me back that numeric vector of where the object is 1. Okay. I can ask what is B. B will say I've got a list, and the elements inside of B are C and D, and it's 2 and 3. If I call the examp $C, it gives me back null, okay? Because C does not exist at the top level of the list. So saying what is C, it gives me back null. It's not NA. NA is a missing value for an object that exists. Here, the object doesn't even exist, so it returns back null. Okay, and so here I got examp $B $C. That thing exists, and that's the value 2. Okay, and then if I say examp $E, then it gives me back the numeric vector 4, 5, and 6. On top of all of this stuff, we have attributes. Okay, attributes, you can kind of think of this as like a sheet that is attached to the object, okay? And the sheet itself is kind of a list. So any object you have, you can attach whatever arbitrary metadata you want to it, okay? The most important ones are class names and dimensions, but we can access the attributes using the attr function or the attributes function. All right, so let's take a look at this, okay? So here I'm creating a vector x, okay, and it's a numeric vector type double, and the things in it are 1, 2, and 3. But I'm giving it names L, M, and N. Okay, the parentheses around the whole thing just says print whatever it is that you created. So normally, when you have an assignment operator, you say take this vector and store it into X. R does not normally print that out, but if you put parentheses around that assignment operator, it will print whatever it is that you just assigned there. Okay. So here X is a vector of the objects of the values 1, 2, 3 with the names L, M, and N. If we ask what are the attributes of X, it says, oh, I've got something called names, and the names are L, M, and N. And we ask what's the structure of attributes. We recognize that the attributes are stored as a list, and there's only one thing in this list right now. It's just the names with a character, and it's a character vector. Okay, and we can access the names directly by using the attr function and say, give me the attribute of X that's called names, and it says, okay, that's the character vector L, M, and N. Okay, we can reassign that, okay, because attributes of X names is currently this character vector L, M, and N, and I can say, you know what, I want to use letters, bracket 1 through 3. You guys know about the letters vector inside R? So R has the inherently built into it a letters vector, okay? Lowercase letter and also all caps letters, and they're just character vectors A through Z, okay? But it's a quick way, if you say, you know, I need the letters A through E or something like that, you just say letters square bracket 1 through 5 or something like that, okay? You don't have to type in quote A, quote B, quote C, quote D, quote E, because that's tedious, right? And there's no quick way to do that otherwise, other than using the letters vector here. So we have this, and so we can reassign the, change the values stored in our attributes by assigning the letters A, B, and C to it, and then we can see X has changed, okay? We can also just create any arbitrary attribute that we want, okay? So if I want to create something called my underscore attribute and store in the string this is a vector, I can do that, and that just gets thrown into my list. Okay, the attributes of an object is just a list, and you can throw whatever object you want in there. You want to throw in a function, you can throw in a function as an attribute to something. That is allowed, okay? You probably don't do that often, but whatever you want to put in here, you can put in there, okay? The most important attributes, though, are names, dim, and class. And so we have our own shortcut functions for those. So instead of having to reference the names by using attribute X, quote, names, you can just get the names quickly by doing names of X, okay? And they're the equivalent, okay? And so we could say, you know, what are the attributes of X? We get the names, all of this, okay? The attributes are lost when the vector is modified, okay? With the exception of names, dimension, and class. So if I modify X just by subsetting it, I say I only want the first element of X, and I ask what are the attributes of that, my attribute gets thrown away, okay? And it just preserves the names. So so generally, yeah, extra attributes other than the names, dimension, and class will get thrown away when you modify. Okay, modifying includes subsetting. Okay, we can modify names. We can create a vector with names in a few ways. We can create the names as we're creating the vector, or we can modify the names in place. So we created the vector X, and then we're going to just say names of X, and we give it the vector of names. Okay. You can also use the function setNames, and this creates a copy of the object X now with the name attributes, okay? And then you can store it someplace. Here I'm storing it as Y, but of course you can always store it back into X, and then it seems like it has changed it, but what it's really doing is it is creating a copy of X with the names, and it's storing that back into X rather than modifying it in place, okay? If names are missing, it will give us missing, okay? And if the names don't exist at all, then it gives us null. So if I say X is 1 through 3, and I ask this, and I ask what are the names of X, it's going to return, what will this return? It's going to return null, okay? And then if I say names of X, I want to be A and B, but X has actually 3 things in it, what's it going to do? Okay, well, if I ask, well, what does X look like now? It's going to say I've got A, B, and then it's missing a name here, okay? So then if I ask, what are the names of X? It will say A, B, and NA. I've got a character vector, same length as X, but where I don't have values, it says missing, okay? And if I really wanted to do it, I could do NA this, okay? And names of X is now this, and the X is this, and I can subset this, and X will give me back that, okay? Is that okay? All right. Okay, yeah, names don't have to be unique, but it is most useful when the names are unique. So if I wanted to, I could also have, this is also allowed, okay? X is this, and if I tried to subset, not. Okay, it only returns back the first one, okay? So that may not be what we want, right? Having unique names is best, but it's not required. Okay, we got factors, and we gotta hurry. So factors, you can take kind of like character data or whatever it is, and you can turn it into a factor. It looks at all of the values, and it says, okay, these are the different values I've seen, and it's basically used for categorical data. You got different groups, and you want to say these are the different groups that exist. You can do that, okay? So you create a factor here, A, B, B, and A, and it does this, okay? And notice when it prints out the factor, there's no quote marks around A, B, B, and A, okay? And that's because it's a factor to distinguish it from a character vector. Factors are stored as integer, okay? If we ask type of X, it's an integer, okay? The class of X is a factor, but underlying the mechanism is that it's being stored as an integer, and those levels, A and B, are stored as attributes of X called levels. So if I create X to be a factor, okay, so X is this, and I ask, what are the attributes of X? What are the attributes of X? You've seen all the attributes of X that we need, okay? The attributes of X are the levels and the class. The class of X is a factor, and the levels are A and B, okay? Okay. When you have a factor and you try to throw in a value that doesn't exist in the thing of levels, it's going to produce an NA, okay? So if I tried to throw in something that's not one of the levels, like this, okay? It's going to say invalid factor level NA generated, okay? So now we get a missing value there. Okay, and you can't combine factors like you want, because if you try to do that, the underlying data types is integer, and so it's going to try to combine those, okay? Because you can't, it doesn't know how to combine levels when it comes to factors. Okay, so factors are useful if you kind of know the possible values that a variable could take. All right, and so in this example, we got 3 m's here, and if you create a table on this character data, it's just going to say I see 3 values of m, okay? If you create a factor and you say I'm expecting the levels m and f, or maybe we have a other or an x or something for the factor, then it will produce the table accordingly, okay? It says I saw 3 m's, but as far as the other levels concerned, I didn't see any of those, or something like that. So that's kind of what happens when we are dealing with a factor, okay? Sometimes when we import our data, things suddenly are turn into factors, and we didn't expect it to become a factor. And so, you use read.csv on something, and then you got a column of numeric values, but when R looks at them, they look like R turns them into a factor. Okay. Oftentimes, what happened in those cases is that one of the values in your column is like a dash or is something to indicate a missing value. Okay. So something, if you have missing values represented with a dash in that column, R is going to see that, and it sees the dash as a character, and it's going to coerce everything in that column to be a character. And then the default behavior for R handling characters is then to treat characters as factors. Okay, so that's what happens. And so in order to avoid that, you can use the argument na.strings, and it tells R, whenever you see this particular character string, turn this, treat that as a missing value. So you say na.strings is equal to the dash. Then R will say, okay, I see the dash. I'm going to interpret that as missing value, na, and then it will work accordingly. Okay. But again, the default behavior of data frames and read.csv or any kind of reading in function, the default behavior there is to treat strings as factors, which back in the day may have been a useful thing because a lot of times people did use have categorical variables that were stored as, as characters. But now often we want to actually do work with the character data itself, right? We have natural language processing is a big thing, and we want to treat things as character data. And so you'll probably want to use the option strings as factors equals false. And that's going to say if you see strings, leave them as strings instead of trying to turn them into factors. All right, and you can always, if you do have categorical data and you want to turn things into factors, you can always import it, add everything as character data, and then go back and explicitly change some of your columns into factors. But a lot of times you should probably leave things as strings, okay? And this slide just talks about the difference between factors and characters. We'll do some text processing later on in the course. So we'll cover regular expressions, which I always think is so cool, and that deals with dealing with strings and character data. And so that will come later. But basically, only use a factor if the thing really is a factor. Okay, so factors being a categorical variable. So if you want to say like you want to store information about the type of vehicle that's being driven, and you're going to say we're only going to accept these 4 vehicle types, or, sedans and trucks and I don't know, whatever else you have, then yes, it makes sense to use it as a factor. Okay, but a lot of other times, if it's something that somebody said, words, that's character data. Okay, we'll stop here for now, okay? And then on Wednesday we'll resume and talk about matrices and arrays and these 2-dimensional data structures. All right, be sure to take a look at your homework and get started there, and we'll see you guys on Wednesday.